Solving a polynomial inequality. We're going to go ahead and solve this polynomial inequality. The polynomial is actually on the left-hand side of the inequality symbol. It has degree 4. That means it has zeros that will add up to multiplicities of 4. And we're going to go ahead and write those zeros out. And we're going to test them around a number line. And we're always going to shade the true side for an inequality. Let's go ahead and get started. So the first thing we want to do is make sure you can get the zeros of your polynomial. So off to the side here, what you're going to do is actually take this polynomial here and find the zeros. So that means we're going to set this equal to 0 and we'll solve for x. Clearly, you can see that your zeros, the farthest left-hand 0 is x equals -8 with multiplicity of 2. We have another 0 at -2, and we have another 0, which is 6. We're going to go ahead and put those zeros on the number line. When we put those zeros there, I'm actually going to highlight them. And so we have a 0 at -8. Don't worry about the scale too much here. Just leave enough room so that you could actually test around the zeros. And so here's the x number line. And we're going to test around the zeros. And we're simply going to use this original inequality to test. Now we need to test a number that is left of -8. So usually what I like to do is choose something far left in the domain, like x equals -100. And what are we testing? We're testing it in this original inequality here. And I don't really care if this is actually positive or negative. Positive means greater than 0. So my work is going to be a little bit shortened. It's more of a conceptual way of seeing things. So when you square the very first number, you always get positive right here. It doesn't matter what x you put in here. So you're going to get positive there. Now remember, x is going to be -100. So -100 plus 2 is negative. And then -100 minus 6 is also negative. So what I'm going to do is write what I call a little bit of bubble math. It's not really math. It's just concepts. It's more concepts than anything else. So I'm going to have a positive times a negative times a negative, which is that in fact, let's say, greater than or equal to 0. And negative times a negative is positive, and then positive times a positive is positive. So this is true. True is good, because that means we actually shade that true side. Let's pick a test point in between -8 and -2. So what can we test here? Test, let's say, it doesn't really matter. I guess you could say you could test x equals -7. And once again, I just want to know, we're going to test the original inequality. So when x is -7, remember the very first one is always going to be positive. Positive. -7 plus 2, if you're wondering where I am, -7 plus 2 is -5, which is negative. -7 minus 6, which is also negative. So once again, we have this similar pattern. We want to know, is this greater than or equal to 0? And the answer is this statement will get you a true statement as well. and we always shade the true side. Why don't we pick an x value between -2 and 6? So a good one here would be x equals 0, right? We're going to test x equals 0 in that triple star inequality. Once again, the very first one, we already know it will get you positive. And then 0 plus 2, 0 plus 2 is positive. And then 0 minus 6 is negative. Is this greater than or equal to 0? And the answer is no. Well, in other words, is this statement true or false? This statement is false. So we do not shade this region of x's. We only shade the true sides. We never shade the false sides. Let's pick an x value in the domain that's to the far right of 6. So why don't we pick x equals, let's say, even 1,000. And you're going to realize that that just yields quickly positive times positive times positive. Is this greater than or equal to 0? And the answer is true. And so we do want to shade this side as well. We are ready to shade. Now, this inequality here, it says this is greater than or equal to 0. Well, that also means we could include our zeros as well in the shading. So we could shade our zeros also. If you don't believe me, you can always check it. You could plug in -8 and ask yourself, does it yield a true statement? If you plug in -8 here, will you yield a true statement? And the answer is yes. If you plug in -2 here, and -2 here, and -2 here, will you yield a true statement? The answer is yes again, and so on and so forth. Why don't we shade all the true values? I'll go ahead and shade. Remember to shade the arrow, and then shade. Anything that's true, we need to shade the 0 as well. Shade the 0. And then shade. So I'm shading from left to right. Then shade the -2 as well. We do not shade the false region. So our next true x value is 6. And once again, we shade from left to right. And make sure you shade the arrow. Now we need to write our answer in interval notation. Once again, the emphasis here is from left to right. So we're going to state all our true x values. -infinity. We include -8. We include -2. So we have up to -2, and we put a bracket. The bracket symbol includes -2. Union, bracket, 6 to infinity. Once again, the emphasis is reading your number line from left to right. Notice this simply transfers to a grammar that is read from left to right. And there you go. You were able to solve a polynomial inequality. I forgot to mention that you should probably circle all your work as well. The work here that you may not want to circle is the aside work. The aside work is a little bit easier. It's just there for you to conceptually understand that you're testing around your zeros on a number line. So you could, you don't have to circle this part. But you do want to show your work here. It's very important to communicate the notation and the mathematics.